Good evening everyone. Today we are going to introduce some new concepts because ultimately we have to learn the electromechanical impedance technique in bit deep sense. So that's why we'll introduce today the concept of mechanical impedance. So I hope my screen and my writing, everything is visible to you all. Alright, because we are using the term mechanical impedance and then we are also using the term electrical impedance or electrical impedance, so it's very important that we have clear understanding. So let's say we begin with a single degree of freedom system. So let's say we have mass element. So this is under a force, a dynamic force, and then we have here the spring element and the dashpot element. Okay, so now we say that this is under a harmonic force and dynamic force. So we'll use the notation that we are representing this force by F0 e to the power j omega t. So we have already learned this concept that how we talk about phasors, that generally we can consider a force such that force is a vector. So when the vector is undergoing a motion like this, we call it as a phasor. So we have, let's say, the force, the amplitude of the force is F0, and we say this is the real axis and this is the imaginary axis, and we assume that this vector is undergoing rotation at an angular frequency, which is the frequency of the force. So at a given time this force was here, and at a given time the force vector is positioned here. So this angle is omega t. So we say that this has two components now. This vector has two components, one in the real plane and the other in the imaginary plane. So the real plane component is basically the cos component, and the imaginary plane, the component is the sine component. Okay, so this is the definition of the phasor, and we represent phasor by this kind of exponential functions. So basically here the complex notation comes into picture, because the moment we say e to the power j omega t, that means we expand, this is basically cos omega t plus j sin omega t. So we say that the force, we can consider either the real component or the imaginary component. We can say that, okay, real component, that is the projection on the real axis, that is the actual force acting at a given instant of time, and the other one we can ignore, or we can do the other way also. So whatever the case, if we are considering the real component, then in the response also we have to look for the real part. So this makes the entire mathematics bit compact. So now if we consider the equation of motion, So we know that we can write very easily the inertial term, then the damping term, and finally the spring or the elastic term, elastic force, and this we equate to the force acting, which is F0 e to power j omega t. Because the force is harmonic, so response will also be harmonic, and we know that when the response is harmonic, so we can express the velocity and the acceleration in terms of displacement. So this we can write that this is j omega times x, and your acceleration is minus omega square x. Okay, so we can now write the equation simplified. So everything in terms of the displacement now, the acceleration term and the velocity term we can convert in displacement, and then we get some compact form. So k and m omega square, they form one component together, and then we have the imaginary component formed by the damping, and outside we can keep x, and we have the force F0 e to power j omega t. So now what do you observe? What will be the solution in terms of x? So the solution will be simply we have the force term and the denominator is not a real number, it's a complex number. Alright, so now what will be the solution? So what will be the output of the solution? Before we work out the solution, let me give you some special case. Special case I give you that, let's say, imagine scenario 1 or case 1, your damping is 0. So if damping is 0, how do you relate the force and the displacement? X is the displacement. So how do you relate the force and displacement if damping is 0?
There shall be no imaginary term.
Right, no imaginary term. But if I ask you in terms of the phase difference between the force and the displacement, what will be your answer?
Sir, there will be always phase difference phi, and I think phi is equal to tan phi is equal to 2 r epsilon by 1 minus r square, something like that.
See, if your imaginary part is 0, yes, any other guess?
It will be in phase because only constant term is changing. The angle is not changing.
So according to you, if we make this term C0, in that case there won't be any phase difference between displacement and force.
Yes, only amplitude also.
Yes, correct.
Oh, sorry sir.
Correct. If we have this condition that C0, then your displacement x will be simply given by very simple expression F0 e to power j omega t, numerator, and the denominator will have again a real term. Alright, so this will be the amplitude of the displacement. This will be your displacement amplitude x0. But what we find in this particular case 1, that there is no phase difference between the force and the displacement, right? You all agree? There won't be any phase difference between force and displacement if damping is 0. But if damping is not 0, in that case what will happen? Case 2, if damping is not 0, then what will happen? That is, damping is not 0, it has some finite value. Then how do you relate the force and displacement with each other in terms of phase? Because in that case, the numerator, which is an exponential function, and the denominator is a complex term, right? Denominator itself is a complex term, so it will have two components. Your displacement will be given by f0 e to power j omega t, and here you have one part which is the equivalent stiffness. I mean this part, the inertial term and the stiffness term, they are combining, and we are denoting by k dash, and then the other part which is representation of the damping, so we can just say it is equal to c dash, we are clubbing omega in that, and then j. Alright, so this is a complex number, so we can write that this is equivalent to so what we are seeing here is a displacement. Displacement is equal to force divided by stiffness. So what we find here, this is like an equivalent stiffness, equivalent complex stiffness, right? This is like a complex stiffness, because when we see the dimensions, we are basically dividing force by something and we are getting something in result in terms of displacement. So this will be equivalent stiffness, so we say it's equal to, we say it's a complex number, so this can always be represented as k equivalent. On the top we have e to the power j omega t, and in the denominator we have e to the power j phi, right? We can always find the value which will match this. So the output will be, now what will be the output? Output will be, I am going to the next page. So in case 2, so your displacement will be equal to f0 divided by the equivalent stiffness, and here we have e to the power j omega t minus phi. So that is for the case 2. So what do you infer here? That x or the displacement will lag behind the force. So what is your conclusion from this? Conclusion from here is that basically why there is a phase lag, a phase difference between the force and the displacement, stress and strain. The main reason is the presence of damping. Okay, so if you are drawing force versus say omega t, I am clubbing omega also here, and we can draw, I am just using blue pen. So if this is your force function, then your displacement function, if I am drawing in the same graph, then your displacement function will be following curve, a different curve like this. So what is this? This is the phase lag. This is basically the phase lag. So the conclusion is that because of damping only we have the phase lag. If damping is not there, then we will not have any phase lag. In displacement terms, so when we say phase lag we are measuring between force and displacement. That's why I have written with respect to displacement. The main cause is, or the only cause is damping. So if damping is not there, there won't be any phase difference. But another point we are finding here is that finally when we are deriving, we are getting something like this. So let's say if we don't have any inertial term, if inertial term was 0, let's say the mass is very negligible. Say if the inertial forces are very small, then essentially we'll have displacement given by like this. Alright, this would be the expression for the displacement. So now the denominator is like an equivalent stiffness. So we can say that stiffness is a complex now. We can say that this is the real part of stiffness and this is the imaginary part of stiffness. So stiffness has become complex. So stiffness, otherwise it was K, but because of the presence of damping, we are getting higher effective stiffness, right? So this introduces the concept of complex Young's modulus. So we can say that, or Young's modulus we can denote like this: K 1 plus eta J. So this is a representation of damping, and we call eta as the mechanical loss factor.
Sir, can you repeat this once again? Complex Young modulus.
So what we are seeing is the damping manifestation is in the form of, see, damping is there. So suppose we represent the damping in this form as a complex Young's modulus. So then this takes care of damping. How? Let me elaborate further. So essentially, if we go like this, let's say we are doing an experiment. So we have elastic bar, and it has a very negligible mass, and we are applying some stress. So stress is dynamic in nature. We are denoting it by sigma naught E bar j omega t. So it's dynamic at frequency omega. So here, what would be the strain? What will be the strain? strain would be your stress divided by the Young's modulus. So if your Young's modulus is, we are just using the normal Young's modulus, what we will get? We'll not get any phase lag. If our Young's modulus is usual, no phase lag. But then if we define our Young's modulus as a complex Young's modulus,
sir, is it sigma E J omega t or sigma 0 E J omega?
oh yeah, top, this has to be sigma naught. Yeah, correct. Sigma naught. Okay. So complex modulus, if we are defining like this, such that this factor eta takes care of the damping itself. So we are including damping in the stiffness itself. Just like we have seen that we are defining stiffness K in the like this, K plus C omega j. This is our now equivalent stiffness, right? Equivalent stiffness. So let's define stiffness in general. If we have this kind of arrangement, then what will be the stiffness? Stiffness K of an elastic bar is nothing but its Young's modulus, area, and divided by the length, right? That's the stiffness. So if we are defining complex Young's modulus, so our stiffness will be Y A by L 1 plus eta j. That will be our equivalent stiffness. And this includes the part from the damping itself. So these two are equivalent. So essentially what we have done is, this is our K. So what we have done is that we have defined Young's modulus as complex Young's modulus, and this takes care of the material damping also. Now you can use, for example, same, if you want to now do the same calculations with this, and instead of the original Young's modulus, you are including the complex Young's modulus. Immediately you will find that there is a phase lag, because now you just multiply and divide by 1 minus eta j, its complex conjugate, and what you get here, the denominator you have one plus eta square, and in the numerator you have sigma naught and 1 minus eta j e to power j omega t. So immediately what you find, you will find that there is a phase lag. How there is phase lag? Because we have an additional term now. In the numerator we have an additional term. So this brings about phase lag. So it has been found, usually the damping is very small. The fractional contribution of damping is very small. That usually we find that this term eta is very small. It's very small. So in the denominator we can just approximate this to 0, n square as 0, and in the numerator we can write it as, this term can be written as e to the power minus j phi, where phi is very small angle. So phi is very small angle. So when you expand e to the power minus j phi, you will get 1 minus eta j, because cos phi, that will be 1 because it's very close to 0. This angle is very close to 0. So cos phi will be 1, and when we say the sin phi, Sin phi will be equal to just eta itself. So in fact, this phi will be equal to the value eta itself. Alright, so we can write this in this form, that this is equal to epsilon naught by y e to the power j omega t minus eta. So that will be the solution of the strain or epsilon. So what do you find? We find that strain will now lag behind stress. So phase difference is created now. This leads to the phase lag. So this is one for representation of damping, and this factor eta is called as the mechanical loss factor. Technically it's called as mechanical loss factor.
Omega t minus theta or omega t minus phi?
See, how can you expand 1 minus eta, for example, this is 1 minus eta j. So if you expand, just try to expand e to the power. You have pen and pencil, everyone? Can you expand this? What we get? If eta is very small, we say that eta has very small value, what do you get? Aniket, what value do we get?
No, sorry.
What value do you get?
E cos eta plus j sin minus.
So this eta is very small. So what we get?
Okay, sir. E to the 1 minus.
1 minus.
Okay.
Right? So that's why we are representing this by this.
In
Hope you understand?
Okay. Yes,
So basically complex Young's modulus is, we always say that the dynamic Young's modulus is higher than the static Young's modulus. What is the reason? What is the reason that the dynamic Young's modulus is higher than the static Young's modulus? So reason is, main component is damping, and of course there are inertial effects also. So whenever we have dynamic situation, so the dynamic Young's modulus will be higher. So we represent the Young's modulus like this. So we are using a term with bar. So any term with bar indicates that it's dynamic, it's complex or dynamic Young's modulus. So in all our derivations, whenever we have a term with a bar, it means that it's dynamic. And now naturally, you know that the dynamic Young's modulus is higher than the static Young's modulus. So it's this factor, mechanical loss factor, that leads to higher value of the complex or the dynamic Young's modulus, right? So any doubt about this? But then my next question is, how is this eta related to the actual damping? See, how related to the actual damping factor C? That is my next question. So basically we have the equation, we have to just look at the equation again, that we have the term here K we have the term K, we have here the stiffness, sorry?
Yeah, eta is equal to C omega by K.
Yes. Are others able to get what Aniketa said? So what we have done is, we have basically introduced here complex stiffness. So we have the stiffness term, one is for the stiffness term, and eta is for the damping term. we are assuming that we are not considering inertial forces right now, we are only considering stiffness and the damping terms. So this is should be equivalent to K plus C omega J. Right, these two should be equivalent. That's how we are going. So that means we can now find the relation between C and the eta. So how the two are related?
K into K into theta is equal to C into omega.
Yes, just we equate these two and we'll be able to get eta as C by K into omega. Right? Right, so this is representation of the damping. So this is also in basically as a fraction. How much fraction of stiffness is represented by damping? So it's in fractional terms. Okay. So always we'll find that if you find the actual value of the Young's modulus. So Young's modulus we have defined like this. So its magnitude will be now higher. It will be y under root 1 plus eta square. So slightly higher than the static value. So basically this representation of damping in terms of the mechanical loss factor, is it totally new for you or did you hear this term before? Have you heard this term before?
No sir, for me I have heard the term first.
Okay. Now let's find out the equivalence. You must have heard of other forms of damping.
Sir, can you repeat this one question? How y into 1 plus s squared is now?
See, or Young's modulus is now. Now our Young's modulus is this. Right? This is our Young's modulus now under dynamic conditions. Complex Young's modulus. So what will be the magnitude? What will be the magnitude? Magnitude will be y,
okay, y
1 plus eta square.
Square root of 1
Right.
plus s square.
Yeah. And we can always write v for j eta. Alright. We can write like this. Where eta is very small value. Okay, so this is the complex Young's modulus. So what other forms of damping you have heard? When we say damping, you are saying that you have heard it for the first time. Let's relate. How does it stand with respect to the other definitions of damping? Any other definition of damping have you heard? See, in dynamics we use the term damping ratio. So what is damping ratio? How do we define damping ratio? This is just a question from your structural dynamics. So we are denoting by the symbol psi. So how do we define damping ratio? So damping ratio is basically the damping related to the critical damping. Right? And what do you mean by critical damping? What is critical damping? What is an underdamped system? What is an overdamped system? And what is a critically damped system?
Sir, when C is equal to C.
When C equal to Cc, then it's what?
No sir, when C is equal to I think 2 into rho e square root of km less than km, then under damping is equal to is a critical damping. I think something like that.
No, physically, what do you mean by under damped system? Physically, what is an under damped system? Sorry?
If we will oscillate, if it will start oscillating, it will never cross the mean position. Like it will always stay in one direction. Like it will take infinite time to come back. Oscillate. Something like that.
Okay, now I am drawing here one system. So is this underdamped or overdamped? This is underdamped system or overdamped system?
Underdamped system.
And another type I draw like this. This is underdamped or overdamped. See, the first system, the damping is less than the critical damping. When the damping is less than critical damping, the structure will undergo vibrations like this. But if it's overdamped system, there won't be any vibrations because the damping is such large that simply you are exciting the structure, it will not undergo physically any vibrations. The first cycle itself it will damp out. So that is an overdamped system. And critically damped system means it's just sufficient to come into oscillations. Okay. So how is critical damping defined? I think Aniket, you are telling some formula. This is the definition of the mathematical expression of the critical damping. Alright. So we can always express, usually what we get for different materials, we are getting the value of the damping ratio. So if we are damping ratio is known to us, we can estimate the damping constant. So we can write C equal to 2m omega n psi. Alright. So if we know the natural frequency of vibration in terms of the angular frequency, so this is basically 2 pi Fn. Okay. So this is one definition of damping. Okay. So how is this related to mechanical loss factor? So my question is that whether you express in terms of the mechanical loss factor eta or you express in terms of the damping ratio, there should be some equivalence. So how the two are related?
Sir, eta is proportional. Eta is equal to C omega by K. If we replace this, C is equal to 2m omega n and into epsilon, where epsilon is the damping.
Okay. So can you find out some relation? Can you find out relation between psi and eta by this?
Eta is equal to 2 psi.
Yes, exactly. Because we have derived earlier that eta, what we have derived eta is basically C omega by K. Alright. And of course when we say omega, we are meaning the natural frequency. Okay, so by this comparison, if you now equate C from both equations, Alright, so we have two expressions for C, and if you now equate, just equate the two, and by equating the two you will get this relation that your eta is 2 times phi. So that is the relationship between mechanical loss factor and the damping ratio. So this damping ratio is based on damping related to the critical damping. So this is called as damping ratio. And this is the mechanical loss factor. So mechanical loss factor basically it makes the complex Young's modulus. So the two are totally equivalent to each other. Okay, there is one more representation of damping. Have you heard of Rayleigh damping? What is Rayleigh damping? How do you define Rayleigh damping? So my next question is, what is Rayleigh damping? So damping is always a mysterious term, very mysterious term, and to simplify, damping is represented in several forms. So Rayleigh damping, it basically expresses damping as a function of the mass and stiffness. So here it's expressed alpha times m plus beta times k. Because damping is mysterious, so to simplify the computations, Rayleigh he expressed damping like this. So this is the mass multiplier and the stiffness multiplier. Alpha is the mass multiplier and beta is the stiffness multiplier. So now if I ask you, now what is the equivalence between Rayleigh damping and mechanical loss factor? Is it related to, how related to? The mechanical loss factor eta. Now why I am doing is because I have introduced a new term. I have introduced a new term, and this new term we will be using in the impedance approach in all the derivations which we will be doing for the derivation of the basic equation of the electromechanical impedance. So my question is, how is this eta now related to the Rayleigh damping? So that's very simple, because we say that in terms of the mechanical loss factor, we can always write that this is C equal to eta k by omega. Alright, so can we find an equivalence between eta and alpha and beta? What will be that equivalence?
Eta is equal to alpha by omega plus beta omega.
Okay, let me reverse the question. That let's say we know the value of eta. Let's say we know the value of eta, then how would you find the value of alpha and beta if eta is given to you?
So it will be a quadratic equation we have to solve, right?
Quadratic, and will there be a unique solution?
So eta is equal to alpha by omega plus beta.
Let me suggest you a very simple solution. Simple solution, that this term eta, it is basically multiplied to what? It's multiplied to stiffness. So it's basically more friendly with the stiffness. So here if you are given eta and you want to find alpha and beta.
Eta by omega is equal to beta.
Eta by
Omega is equivalent to beta.
But in that case,
eta by omega is equivalent to beta.
but how about alpha? Suppose I give you alpha and beta. If I give you alpha and beta, and if the values of the m and k are known, you can find out the eta, right? Then it's a simple. But now I have given you a difficult problem that if eta is given, how would you find the equivalent values of alpha and beta? And will there be a unique solution? The answer is that there won't be a unique solution. But one possible solution I am telling you, that you choose this simplified solution that alpha is 0 and beta is eta by omega. This is one possible solution. Okay, that your mass multiplier we are taking 0 and the stiffness multiplier we are taking like this. So now frequency has also come into picture. So it depends on what is our excitation frequency. Alright, so this is one solution. And now let me also ask you a question, that how do we find another let's say relation. Your damping ratio xi and your Rayleigh damping alpha and beta. So one solution you know, because your eta is 2 times xi. So one solution you already know, that simply we can make alpha as 0 and we find out the equivalent of beta, just like in the case of the mechanical loss factor. But I will give you another solution, a different solution, that let's say we have a frequency range. We are operating in a frequency range. Now why I say frequency range? Because in the EMI technique we always talk of frequency range. Okay, so let's say we are talking about a frequency range so that we get a unique solution, and in that unique solution we don't want alpha 0. So let frequency of operation be from F1 to F2. It's a range because damping also depends on the frequency. Okay. So now we have let's use the two definitions. We have the C here, and on one side we have the Rayleigh damping. So Rayleigh damping we are writing alpha m plus beta k, and on the other side we have the damping ratio 2m omega xi. Okay, so we are making one approximation that we are generally this is valid for, this should be the natural frequency, right? So we will assume that this is valid at all frequencies. At all frequencies, though this is valid only at the natural frequency, but we assume that all frequencies which are in the range F1 to F2. That is our assumption. Now you can find it very easily. Just you divide both sides by 2m omega. So for us, omega and omega n we are using interchangeably. It does not matter whether it's omega or omega n, both are same we are assuming, that's what. So if we do that, what do we get? 2m omega, so we get here alpha by 2 omega, And what do we get here? Beta omega by 2. You can just verify yourself, and on this side we have simply xi. Right, so this term no issues. I think you are simply dividing by 2m omega. So m is cancelling out and omega is here. And how do we get this? You have to write k. That's very easy. All you have to do is just substitute omega as under root k by m. If you do this substitution, you will get this term. Just try it out. So everyone is able to get this?
Yes.
Okay. Now we'll have a unique solution.
Sir, what we
Sorry?
Sir, what we assume this equation is valid for all frequency and damping.
Yes. That's our assumption. See, this definition, when we say here omega is basically the natural frequency of the system, the undamped natural frequency of the system. So we are assuming that this equation is valid across the entire range. Okay. So the range of frequency is f1, f2. So we can express this like this: 4 pi f, and here also pi f, beta pi f equal to psi. Right, so I hope everyone can reach this expression. Now we are giving you the inverse problem that this is known to us. This is known. So xi is known, and I am asking you to find out what are the values of alpha and beta. So we have two unknowns, so we need two equations. Then only we will have unique solution. Otherwise, there are infinite solutions. You have to satisfy this condition. Then you have infinite combinations of alpha and beta. So what we do to get a unique solution, we write this in two equations. One equation for f1, other for f2. So we have two equations: alpha 4 pi f1 plus beta pi f1 equal to xi. This is one equation, and the other equation is alpha 4 pi f2 plus beta pi f2 equal to xi. And we can always say, because xi and eta, they are related, right? Xi and eta are also related. You have seen that basically xi is one half of the mechanical loss factor, right? So if mechanical loss factor or your damping ratio is known, then you can always find the equivalent values of alpha and beta. Just solve these equations and you will have unique values of alpha and beta. Okay, so what I've basically introduced today is a new term, mechanical loss factor, and I've also shown that mechanical loss factor is not anything strange. It's related to the well-known representations of damping, the damping ratio as well as the Rayleigh damping coefficients. So is this clear? I hope this is clear. So now if this is clear, I take you further and I take you to the mechanical impedance approach.
I have one call outside.
Yes,
Can we just
sure.
take here the use of omega
Yes.
and then omega is equal to omega n. And we know that f omega is 2 pi f.
Yeah.
And f is in the frequency range of kilohertz or hertz.
Yeah.
So here what would be the unit of W?
Omega is radians per second. Radians per second. Omega will be in radians per second and F will be in hertz. Omega is 2 pi F, so omega is in radians per second. Right? Yeah. So let's now introduce the mechanical impedance approach. So mechanical impedance approach, it simplifies. Why we are introducing mechanical impedance approach? Because in the EMI technique it does a lot of simplification. It basically reduces a differential equation it simplifies the mathematics. It reduces a differential equation into a simply algebraic equation. And this is very expedient in the case of the EMI technique. We will study it in relation to the EMI technique. So what we are doing today, we are forming the background for the EMI technique. We will derive the complete equation, the governing equation of the EMI technique, and that's why we have introduced something damping. So we have seen that if there is damping in the system, then the displacement and the strain, they will lag behind the force or the stress. If there is no damping, then it will be in phase, no lag. Alright. So let's say we have here a system, again the same system. I am bringing that we have the mass M, and this mass is connected to a rigid support system with two elements in between the stiffness
There is some lag.
and the damping. Lag is where? Is it video lag or audio lag?
Sir, actually video lag and video lag mainly.
Means when I am speaking something, you are hearing me first and you are able to see the what I draw a little later, right?
Yes sir, yes sir. After your writing, then it is visible to us.
Okay, but finally nothing is cut, right? Nothing is cut.
Yes sir, yes sir.
If something is cut, then is a problem. If nothing is cut, then then no issues, right?
Yes, sir.
So since nothing is cut, so we are taking it for granted that there is a lag. So this system I have drawn a single degree of freedom system, the three elements K, C and M, and we are used to the differential equation, but I'll take you to a new concept, impedance concept. So this will also be a new concept, just like I have introduced here the complex Young's modulus. Did you come across complex Young's modulus before? Or are you hearing for the first time? Did any one of you hear about complex Young's modulus before? Or are you hearing for the first time? Aniket? Have you got what I am?
No sir, I am also first time.
First time, yes. So there are many things which you come across first time and they might appear strange. So I introduced the concept of the complex Young's modulus and brought here a new term, mechanical loss factor. But then to show you that it's nothing unusual, I equated it with the well-known forms of damping. So now similarly I introduce now the concept of mechanical impedance. Alright. So here the force is there, so we can write the differential equation. So our purpose is to make everything algebraic. So once you are familiar with the impedance concept, many of the things they will be highly simplified for you, and especially when we say highly simplified, the interpretation will be highly simplified, and then you can physically interpret some processes or some phenomena like damage. Okay, so we have here the force, and this force we are writing in terms of the differential equation of motion. Alright. Now we have here acceleration, we have here velocity, and we have the displacement. In the previous derivation, what I did, I expressed acceleration and velocity in terms of displacement. Right? Now what I do, I am choosing displacement as my base, and I will express the displacement and acceleration in terms of velocity. So how do we define displacement in terms of velocity? We can always write, if everything is harmonic, we can write the displacement as x dot by g omega. Right? Displacement can be written like this, and similarly your acceleration can be written as, right? So can I make these substitutions here in the equation? So let's make these substitutions. So what do we get? We are here now, F is equal to, now what we find is that everything is in terms of the velocity. So we have C, we are writing C first, then we are writing the terms with J. So we have here M omega minus K by omega J, and I have taken the velocity x dot s common. Can I write like this? Why minus sign has come here? Because J I have taken it from denominator to numerator. Just multiply and divide by J. So in the denominator, J square will be minus 1. Alright? So now I can write, so remember here I am expressing everything in terms of only force and velocity. So remember, now no more displacement. Now we'll talk of velocity only. Okay. So this term now, what we get here, what is this term now? We are getting something. Earlier, when we were expressing everything in terms of displacement, we were saying that we are getting some kind of equivalent stiffness. Now we are getting something else. So what is this?
Equivalent damping.
Yes, equivalent damping, and this is called as impedance, mechanical impedance. The complete term for this is mechanical impedance, and you are correct. It's like an equivalent damping of the system, because everything is related to velocity. Mass we have changed and the stiffness we have changed, such that everything is in terms of C, the damping. So damping is the king here, So that's why we are using the term mechanical impedance for this. Alright. So how do we solve this equation? Is there any solution for this equation? Before we solve this equation, I will show you something. I'll write this equation in a different form so that you can very easily use the complex algebra. What I do is that I write like this.
So F is equal to Cx dash x dot.
Yes, C x dot, and then what I do, I write the next term So this equation I have opened like this. Now I am just bringing them together. Now in everything we have velocity. So this is the damping term. This is the inertial term. And this is the stiffness term. So I can say that suppose there was no inertial term, no stiffness term. If the inertial terms were 0 and the stiffness terms were 0, what would you have got? If these two terms are 0, yes, but fine, absolutely fine. But what would you say in terms of the phase lag? If, for example, the inertial terms and the stiffness term they are 0, then I would say that the response, which here is velocity, will be in phase with force. Am I right? Because if the inertial term and the stiffness terms they are 0, then I can say with confidence, 100% confidence, that the velocity, which is the response, will be in phase with force. Can I say? Yes or no? Because here we don't have a complex number, we have a real term C. So whatever is the phase of the force, same will be the phase of the velocity. Right?
Yes.
And let's say if I only have the inertial term. If I only have the inertial term, I don't have any damping term and I don't have any stiffness term.
Yes.
In this case, what would happen now here? In that case, what will be the phase difference between the force and the velocity?
Velocity will lag by.
velocity will lag force by pi by 2, right? Right? In that case, force will, in other words, force will lead the velocity by pi by 2. I can say in this manner also. Yes, absolutely fine. You are all coming in the right direction. And suppose the stiffness term is if only pure stiffness is there, no mass, no damping. In that case, what would be the phase difference? In that case,
The minus pi will.
in that case, what will lead or what will lag? Which will lead what? In that case, velocity will lead. Velocity will lead then. Velocity will lead the force by pi by 2. Right? Right. So now I say that this is the damping force. Damping force is always in phase with the velocity. This damping force is always in phase with velocity. This is the inertial force. Inertial force always leads the velocity by pi by 2. Right, because this is the inertial force. So whatever is the phase of the velocity, the phase of the force, because there will be a multiplier here, so it always leads the velocity by pi by 2. And then the stiffness force. So the stiffness force, it lags behind the velocity by pi by 2. Alright. So we can have a perfect phasor solution for this. Phasor solution, just like we have the phasor diagrams, we can always draw the phasor diagram here, that if we have the velocity on this plane, then the damping force is in phase with the velocity. So damping force I represent like this here, and I call it as the okay. So what I say that the damping force I write like this. So damping force is always in phase with velocity because they are related by a constant. So I can draw the damping force like this. Can I draw? Next we have the inertial force. So inertial force I write like this: m omega e to power j by 2 pi by 2 j x. So the inertial force, it leads the velocity by pi by 2. Right? Whatever is the phase of the velocity, the phase of the inertial force will be pi by 2 ahead of the velocity, because pi by 2 will always add. If this is e to power j omega t, let's say this is x naught dot e to power j omega t, then when we are writing the expression for the inertial force, there will always be an addition of pi by 2. So we say that the inertial force will always lead the velocity. So I am drawing inertial force like this. So this is inertial force. So clear till now? And finally the elastic force, or the stiffness related force, which is K by omega So this will always lag behind the velocity by an angle of pi by 2. So if this is the the phasor of the damping force, the phasor of the elastic force will be like this, lag behind. Is it clear? So, and any disturbance till now, or is it clear?
It is fine.
It is fine. So now we can do algebraic manipulation. All we have to do is the Fi, the inertial force and the elastic force, they are always opposing in nature. They are always opposing in nature. So they will tend to balance each other, counterbalance each other. Okay. So the resultant, we can say the resultant force we can draw. So I can redraw this phasor like this. So here we have the damping force, and here we have the resultant from the elastic and the inertial forces. Correct? So what would be the resultant? What would be the resultant? This would be the resultant. This would be the resultant. Alright. So the resultant force, I am just changing now the sheet. So the resultant force I can write will be simply equal to alright. Okay, so this is now the resultant. And this will be at an angle phi with the velocity. So can you find an expression for this? What will be the expression Fr? If you input here the expressions, so you will find that this is equal to this would be the expression, and this angle phi will be simply tan inverse alright. So here we have the force, here we have velocity, and this is the phase difference. any doubt in these expressions?
No, sir.
So now this concept is very similar to the electrical concept. Why we are using the term impedance? Because this concept is very similar to the electrical concept. Electrical concept, we have the LCR system. I hope you can recall that in the case of the LCR system, we have the resistance, we have the inductance, and we have the capacitance. So together these elements they form an electrical impedance. We say Z electrical, that is equal to R plus L omega minus 1 by C omega J. Right? So this concept of the impedance, mechanical impedance, which we have introduced, is very similar to this concept of the LCR circuits. So LCR circuits also we have same. Now here in our case we have this system. We have this system, and the equivalent expression is like this. Now you just see, compare the two systems. So we have this system. I'm just zooming out so that you can see everything. Yeah. Now I hope you are able to see both the systems. We have the LCR circuit, where we find out the electrical impedance consists of the resistance part, and we have the other part, and similarly we have the mechanical impedance. So this we are using the simple Z or Zm also you can use, doesn't matter, to distinguish it from the electrical. Now do you see some comparison between the two? Do you see any comparison between the two? Any similarity or any analogy between the two?
Sir, here damping is the resistance. M omega minus A by omega is equal to N omega minus 1 by C.
Exactly. Now here this C should not be confused with the damping. This C is the capacitance. Right? This is the capacitance. And what is L called? What is L called? Inductance. Yes. This is just recapitulation of your 10 plus 2 physics. So now the two are very similar. So in the mechanical domain, your damping is very much like your resistance. It is the dissipative component. Alright. So your damping, I am just writing here, damping is equivalent to resistance. Then your mass or the inertial forces, inertial terms, mass is equivalent to your inductance, and the stiffness is equivalent to capacitance. Right? So that's why we have the term impedance. Why we have introduced here the term impedance? Because here we have the parameter velocity, and velocity in the case of the electrical circuits, velocity is replaced by current. So the equivalent of the velocity is now current. So current is basically this is equivalent to velocity. And what is the equivalence of force? The equivalence of force is basically the voltage. Voltage is the equivalence of force. Alright. Now, what is the advantage of this concept? Let me tell you why this concept is advantageous. Many of the things they are highly simplified by the impedance concept. So before that, let's define formally what is impedance. But what you have seen so far, that if you have a single degree of freedom system, then we can write the expression for impedance as follows. That for a single degree of freedom system, the mechanical impedance Zm I am using is equal to C plus so it is a complex term now. It has the real component and the imaginary component. So the real component is formed by the damping term and the imaginary component is formed by the combination of the mass and the stiffness terms. And what is the magnitude of the mechanical impedance? Magnitude is simply, we have to just use the complex algebra and we get C square plus m omega minus k by omega whole square. So this is the magnitude. And if we have we are applying some force, then the resulting velocity will have phase difference with the applied force, and the phase difference will be given by okay. Now let me ask you, how can we define mechanical impedance? Is there any way we can define mechanical impedance?
Sir, your screen is freeze.
Is my screen frozen?
I can see the.
Okay, let me share again. Are you able to see the screen?
Yes.
So now we have to define the mechanical impedance, because we have seen that if we have force, then force is basically equal to the mechanical impedance, which should be a complex number multiplied by the velocity. Okay? So how we can define mechanical impedance? How can we define mechanical impedance?
Is the force component unit velocity?
Exactly, yes. So basically, when we say mechanical impedance, first of all we have to define where we are applying force and where we are measuring the velocity. Let's say we are applying force at some particular point, a dynamic force, and this point is I, and we are measuring velocity at some other point, which is J. Okay, velocity is being measured here in the direction of the force. So basically, your mechanical impedance Z, we will say that it is now Zij. It is Zij. The 2 points are there. I is the point where we are applying force, and J is the point where we are measuring the displacement. So this is basically equal to the ratio of force applied at I with respect to velocity in direction of force at J. Yes. So is this clear? This is our definition of mechanical impedance. So how we have defined? It is basically equal to we are using the subscript Fi and Xi. So Zij is basically Fi by X dot J. So this is Zij. And if you want, you can use M also to signify its mechanical impedance. But even if we don't use, then that's also understood that we are talking about mechanical impedance. So now my question is that, okay, let me just ask you a question. When we are talking about the phase lag, we see that if there is no inertial term or no elastic term, there won't be any phase lag between the force and the velocity. Right? If there is no inertial term or no, and also no stiffness term, no inertial term and no elastic term, then there won't be any phase lag between the force and velocity. But if there is inertial term and stiffness term, then phase difference will be created. Okay? And phase difference is given by this expression. Now another question is that what happens at resonance? What happens to mechanical impedance at resonance? So here we are considering the single degree of freedom system. What will happen to the mechanical impedance at resonance? Will it be maximum or minimum?
Minimum.
See, at resonance, what will happen? The inertial force and the elastic force, they will counterbalance each other. So this term will be 0 because K will be M into omega square. So this term will be 0. So at resonance, Zm is minimum. The mechanical impedance will be minimum. And there will be no phase lag between the force and the velocity. So phase lag will be 0 at resonance. Okay? Now, with this definition, I will introduce some things, because when we are introducing a concept, there is a purpose. The purpose is to make our computations faster with this concept. So we have to introduce what happens when we are connecting impedances in parallel or series. So when we say impedance, we will use a box. Just like springs, how do we denote spring? We denote spring by this symbol. And similarly damper we denote by this symbol. So impedance we are denoting by this symbol, box. Box with Z written, that is an impedance. So when we say impedance, it includes the contribution of all types of elements. It includes the contribution of the spring, it includes the contribution of the mass and damping also. Okay. So let's say we have two impedances in parallel. Okay. And now here we are applying the force. will be the common? What will be now the equivalent or the resultant impedance? What will be the resultant impedance? So this is a parallel combination. So how do we find the resultant impedance? So resultant, all we have to do is just make a free body diagram. So we have this connection. So at one side we are applying this force. And that is F. And on the other side we have the the two reactions. Just we have drawn the free body diagram. I hope my voice is clear now and no lags. I hope my voice is clear, everything is clear. So all now we have to do is just see this. So basically your F is F1 plus F2. Both the impedances which are in parallel, what will be common in them? They both will have same velocity. Velocity will be same. Right. So velocity will be same. So we can represent the entire thing like this, that we have the first impedance and the second impedance. So that is Z1 into X dot plus Z2 into X dot. So velocity is same. Alright. So we say that this is equal to Z1 plus Z2 X dot. So what is now this? This is the resultant impedance. So that means what we have found, that if impedances are connected in parallel, they are additive in nature. Right? So if I give you n impedances, then your Z equivalent for parallel case will be summation. I hope this is all visible to everyone and I am audible. Hope no break, nothing.
Yes.
Okay.
Visible and audible.
Okay.
Sir, Z equivalent is summation.
Yes. If the impedances are in parallel, then the equivalent impedance will be algebraic sum. Right? The equivalent will be algebraic sum, and if they are in series, then what will happen? So if we have the impedances which are in series, then what will happen? Let's say we have the two impedances like this. And here we have the force acting F. Now what will be the equivalent impedance? How do you find the Z equivalent? Any guess?
Sir, I need x1 plus x2 equal to x equivalent.
Yes. Good intuition. So how do we derive? let's say we have this point as 0, this point as 1 and this point as 2. So basically what is adding now, the displacement is being added. So we say that the absolute displacement at point 2 x2, which is the displacement at point 2, is basically sum of these two. That is, we have the relative displacement between 0 and 1 and we have the relative displacement between 1 and 2. So can we write like this? So this is the absolute displacement. And x01 is the relative displacement between points 1 and 2 and x12 is between points 1 and 2. Means x01 is between 0 and 1, x12 is between 1 and 2. Can you write like this? So let's differentiate. So differentiating we get okay. But now we use the definition of the mechanical impedance. So this is basically because same force, you cut the section anywhere, same force will be acting on both the impedances. Alright, so this we can write as force divided by Z1 and this can be written as force divided by Z2 and this can be written as force divided by Z equivalent. So you have rightly said that in this case if we have series combination, then 1 by Z equivalent is equal to summation of 1 by Zi. So that is the series combination. So is this clear so far? Now the last concluding thing is that if I ask you what is the mechanical impedance of a spring, what will be its mechanical impedance? Mechanical impedance of a spring. All you have to do is just see the constitutive relation. If you are applying force across a spring, always you will find that force is related to the spring stiffness K by the displacement. Right? And we can write this as F equal to K and we have the velocity by G omega. So by definition of the mechanical impedance, this is our Z. So that means Z for a spring is equal to K by J omega, or we take J up minus K J by omega. Alright, that is the mechanical impedance of spring. Now, if I ask you what is the mechanical impedance of a damper? What will be the mechanical impedance of a damper? Mechanical impedance of damper will simply C. Because here what is the constitutive equation? That force is equal to C into x naught. So by definition, the damping constant is the mechanical impedance. And similarly, when we say a mass is there, what will be the mechanical impedance of a mass? So what is the force acceleration relation in a case of a mass? Force is related to mass times acceleration, right? So that we can write as m omega with j and x dot, right? So by definition, this is the mechanical impedance of a mass, that is equal to m omega j. Okay, so that's how we can find. Now there is a difference here in the representation, that when we are doing the classical mechanics, classical mechanics we are representing a single degree of freedom system like this. This is our representation of a single degree of freedom in classical mechanics. But in impedance approach, we represent it like this. We'll show like this, that we have a spring, element like this, the mass element is like this now, and then the damper or the dashpot. So the impedance representation will be different. See, this is the physical representation, that mass is there and mass is tied by spring and a damper, dashpot. So when we draw the same in the case of the impedance theory, our representation will be like this. We will say that stiffness, mass and damper, they are connected in parallel. It's a parallel combination. Okay. So by our definition, what will be the mechanical impedance? Because these are in parallel, so they must be additive. So Z equivalent or Z resultant will be the mechanical impedance of the mass, the damper and the spring. So what is the mechanical impedance of the damper? We have just now derived C. What is the mechanical impedance of the mass? That is M omega with J. And what is that for spring? K by omega. So very quickly, just by using the concept of mechanical impedance, we can find what is the equivalent impedance of this particular combination. Alright. So hope this is clear to everyone. So I give you an exercise before ending. I give you an exercise. Find out the equivalent mechanical impedance of this system. We have the K, the mass and the damper in series. Resultant or equivalent. Okay, so I stop here. If you have any doubt or anything with the impedance concept, you can ask question. Anything which is not clear, so please feel free to ask. So everything is clear? Any doubt, any question? I can repeat.
I don't think I mean.
Yeah, sure. Please take.
Let them ask.
I think no question. Today I use this method. I don't know which one is better. Whether the presentation mode is better or this is better, I don't know. Give feedback. You have to give the feedback. This is better, okay? Because next lecture also we'll do the full derivation now. We'll do full derivation of the equation of the Warning equation of the EMI technique. So we have close to 3 lectures. We have 3 lectures left now. 3 weeks. Before the major, we have only 3 weeks left. So we'll have the 3 lectures. So one lecture will be on the derivation. Then one lecture will be on further applications, and one lecture will be on the non-destructive evaluation techniques. Okay. So you have any doubt or any question, just raise your hand.
Yes, one. I will say one. one lecture on my work which I have done.
Yes. So what we are planning is, Dr. Dhawan, they have in their evaluation system, they have to make a presentation. They have to find some topic, everyone, and everyone has to make a presentation. So now you are gearing up. You have done some understanding of the structural health monitoring. So look for the literature, and if you find something interesting, you can share with everyone. So in that presentation, Dr. Dhawan will present his work, and you all can also present your works.
Right.
So that we have kept certain marks for that.
In addition to that, what is the role of the Indian district secretary? Whether to talk to the parliament, which day and which time, as I told you that we have to talk to him and say, fix up the date and time and the meeting place. Will you do that today?
Yes, suggested something to me. He has suggested 23rd March. Right? Yeah.
He should talk to that party manager.
Yes.
He should tell us which day and when time.
Yes, so what we'll do? Yeah. So basically, I will also call, and then I hope before we call, 23rd March is fine with everyone. Okay, so 23rd March is Wednesday.
Wednesday.
Yeah. So on that week we will not have lab. So basically, this visit is in lieu of the lab.
So he's going to fix up the date and time with the environment. And he to recruit somebody. So now we just say that you can talk to him and fix up this and date and time.
So regarding the attendance, I see most of you are here. I see 28. So if I am not wrong, Archit Kadiyar and Ritik Verma, they have left the course. Archit Kadiyar and Ritik Verma have left the course. Right?
Ritik have left, so I don't know about that.
Archit is also, because both of them they were absent in the minor exam also. So I'm assuming that they have left. And other than that, everyone is present, it seems. I cannot see Veba Bihani, are you there? I think today only Veba Bihani is absent, rest all are present. Okay, then I think we call off the meeting today. So we'll finalize. I'll talk with the chief engineer and then we'll finalize the schedule. So good night to everyone.
Okay, good night everyone.
Thank you, sir.
Thank you, sir.